Okay, so we're going to continue on, and there's just a tiny bit of stuff I want to wrap up regarding confidence intervals. So the first few slides in today's lecture will be the same slides that I finished Monday's lecture with, but or at least some of these slides will be, but I think that's okay. All right, so just to review, the sampling distribution. The sampling distribution is the distribution of all possible sample statistics along with their probabilities. So, we look at, it shows us, basically the probability that a random sample can produce a particular value for the sample statistic. And so what we were looking at is, say, the proportion that can appear in a random sample. And there's actually a little web applet that kind of illustrates this, okay? And I'll go here and I'll run the applet, okay? And basically, I'm gonna just enter a few numbers here. And this is going to be kind of a demonstration of how we can kind of build up a sampling distribution, okay? And so this red box here represents, is supposed to be a candy machine, okay, of Reese's Pieces candies. And if you've never had Reese's Pieces candies, they're kind of like M&M candies. They're these tiny little things, but they only come in 3 colors, orange, yellow, and brown. And we get to specify what proportion of candies in here are orange. And so I'm going to say that in this giant kind of tub or vat of candies in the giant machine, 30%, exactly 30% of the candies are orange, okay? And then, and to illustrate the creation of a sampling distribution, what I'm going to do is I'm going to draw a random sample of 40 pieces of candy, okay? And so it goes to the machine and it's spitting out pieces of candy, okay? And out of 40 pieces of candy, 10 happen to be orange and the other 30 are yellow or brown, okay? And what we're gonna do is we're gonna keep track of the proportion of orange pieces of candy, okay? So out of 40, 10 are orange, and so the proportion that is orange is gonna be 0.25. 10 out of 40 is 25% orange. And what we're going to do is we're going to put a little dot. We're going to build up a dot plot down here to kind of represent our sampling distribution. Okay, and I'm going to do this again. So here's another 40 pieces of candy. Every time we get an orange piece, we're going to throw it over here. Okay, this time, by random chance, only 8 out of 40 were orange, and so my p-hat, my proportion orange is 20%, okay? So, wait, yeah, 8 out of 40 is 20%, okay? And so I put a little dot at 20%. This time we get 13 pieces out of 40 are orange, and 13 divided by 40 is 0.325. We're going to put a dot at 0.325, okay? And let me speed things up. Okay, so this time 12 out of 40 is 30%, and we put a dot at 30, okay? And we can do this again, and here is 15 out of 40. This one is 8 out of 40. And so just by random chance, here's 9 out of 40, 11 out of 40, so p-hat is 0.325, okay? And every time I do this, a new dot will appear down here, okay? All right, and so I can keep clicking, and we'll build up kind of just the different p-hats that we've seen, okay? And so sometimes, some of these, so after running this 20 times, it looks like we saw, 30% 2 times, 20% 2 times, 25% once, and things like that. Okay, I'm going to go ahead and I can do say like 10 at a time. Okay, And what this will do is it will just draw 10 samples and just add 10 dots to our sampling distribution. So this is kind of what our sampling distribution, what the distribution looks like after 100 draws, okay? And what we know is that from the law of large numbers that the more trials we run, the more our empirical distribution will look like the theoretic distribution, okay? So I can keep kind of adding more and more and more. And as we draw more and more samples, we can see kind of our distribution getting more and more dots. Eventually what's going to happen is that the dots are going to get so close together that they just kind of merge into lines, okay? To speed things up, I'm going to draw 100 samples of 40 at a time, okay? So when I click this, we're doing a sample of 40 and we're counting how many are orange and calculating the proportion orange, and we're gonna plot this in our sampling distribution. But to kind of just speed things up, I'm going to just have the computer do 100 all at once, and it's going to add 100 dots. It's going to add 100 dots right here to our graph, okay? So there's, it added 100 dots here, so there's 300 dots total. Here's 400 dots total, 500, and we can see at 500, the dots are kind of merging into each other into a single line. And by the time we get to around, right here, they're just all kind of merged, okay? And what we see is something that's beginning to look like the normal distribution, where values near the middle are the tallest, okay, meaning these occurred the most frequently, and values that are far above and far below occur much less frequently, okay? So, as expected, when you have 30% in the population to be orange, when you draw random samples, values that are close to 30% are most common. And then, values that are way above 30% or way below 30% are much less common, okay? And so if I keep doing this, eventually we're gonna get something that resembles the normal distribution. You can actually overlay the normal approximation over this. And again, the reason why it doesn't line up perfectly right now is because this is the result of actual random trials. This is an empirical, the black lines are an empirical sampling distribution, meaning that they are based on the actual kind of random simulations that we've done. And from the law of large numbers, we know that the more random samples I do, the closer it's going to match the theoretic, okay? The exact theoretic is technically the binomial, and what we're saying is that the binomial can be approximated with the normal distribution. So I'm going to just go ahead and do like 1,000 samples. And so here we are after, say, 7,000 samples, and we can see that the empirical distribution does now match the theoretic distribution quite closely. And that theoretic distribution can be approximated with the normal distribution. And that forms kind of the foundation for all of our statistical inference methods that, when we do a confidence interval, that's based on the normal distribution. When we're going to do hypothesis tests today, and that's also going to be based on the normal distribution. And the reason why we use the normal distribution is because using the normal distribution, the calculations are quite easy to do, and we know that the sampling distribution can be approximated with the normal distribution. It's not exactly, technically the sampling distribution is binomial with all of these lines, but when n is large, that the sampling distribution can be approximated with the normal distribution. And and it gets us close enough to the right answer that we can use that. Okay. All right. So these slides are all kind of just an illustration of us building up the sampling distribution. Okay. And you can even try taking samples of different size. So here I took samples of 40, but if I did samples of say 80, okay, we would see a similar distribution, but with less, because there's 80 of them, the lines are a lot closer together, and the overall amount of spread is a lot smaller, right? So you can try, if I take only samples of size 10, we're going to get something between 0 and 70% orange and things like that. So, but anyway, this is a little app. It's linked in the notes, and you can play around with it if you want. I've also just kind of put some pictures in here, just showing how the sampling distribution is getting built up. So when I ran it, the first time I ran it, I got 9 out of 40, which is 0.225, and I put a dot right there. And more dots get built, and as we did more and more simulations, the empirical distribution starts to look more like the theoretic. Okay, and the central limit theorem says that we can approximate the binomial with the normal distribution. Okay, and when you approximate it with the normal distribution, it's going to have these properties, that the mean is going to be equal to p, which is the proportion that exists in the population, and the standard deviation, or the standard error of that sampling distribution, will have this value, the square root of p times 1 minus p divided by n. Okay, and we looked at confidence intervals on Monday, and the reasoning behind a confidence interval is that we know that our sample proportion p hat comes from a normal distribution, which means that whatever values, when you draw values from the normal distribution, most of the time the values are close to the mean. So most of the time we know that when we draw a random sample, p hat is close to the mean, which in our case is the population proportion p. So even when we're doing a confidence interval, even though we cannot observe the population proportion p directly, instead we are observing only a sample. Even though we see only a sample, when we observe a p hat, we can be confident, 95% confident, that the population proportion is about within two standard errors of that p hat that we've observed. And I gave you this formula, and we said p hat plus or minus the critical value z star multiplied by the standard error is going to form our confidence interval. Okay, the part that we do plus or minus, that's also known as the margin of error, and then depending on our confidence level, that will determine the z star that we use. If you want to be more confident, you've got to make a wider interval, and you're going to use a larger z star. And if you are willing to trade away confidence and make a smaller you can then make a smaller interval using a smaller z star, like 1.28 for an 80% confidence level. All right. And so the example that I ran on Monday was that we said we took a sample of 100 randomly selected people, and in that sample 30 people paid for Netflix. And so we want to know, what's the proportion of Netflix subscribers? And, we did the calculations. You just kind of plug in the numbers that you have. And the conclusion is that the confidence interval goes from basically 21% to 39%. And we say that, I'm 95% confident that the proportion of Netflix subscribers in the population is between 21 and 39%. And I think we've already gone through these interpretations, but basically we can be confident that the population proportion, again, remember what we're trying to do is we're trying to make conclusion about the population, which is this big entity that we're not able to observe directly. We're trying to make a conclusion about that population based on a single sample of, say, 100, 100 observations here. Okay, and when our sample is 30%, we can be confident that in the population, that value is somewhere around 30%. And here it's basically, we're confident, 95% confident that it's 30% plus or minus 9%. So we're confident that it's between 21 and 39%. And so any value that's outside of that range, that anything that's lower than 21% or higher than 39%, we can be confident that the proportion is not that. So can we be, do we have evidence that it's not 20%? Yeah, we can say it's not 20%, okay? Meanwhile, anything within that range, between 21 and 39%, we can't dispute, we can't refute that, okay? So if somebody says, do we have evidence that it's different from 25%? We have to say, we don't have evidence that it's not 25%, okay? We don't have evidence that it's not 25%, but at the same time, we're not allowed to say that we have evidence that it is 25%, okay? We're not saying that it's not 25%, but we can't say that it is 25% either, okay? It's a whole bunch of double negatives, but that's the nature of statistics. We're very, statisticians are very loath to say that the proportion is exactly equal to some value, okay? All we can say is that, we're confident that it's not this, and anything between here and here, maybe it could be, but we're not going to pick any one of those values. All right. The other thing that I mentioned was that if you wanted to be more confident that the unknown value P is within your interval, if you want a higher level of confidence, you've got to make your interval wider, okay? And that's reflected in the choice of the Z star, the critical value Z. Higher levels of confidence require a larger Z star, which make a wider interval. And if you want a narrower interval, which is more useful because it gives you kind of a more precise range, a smaller range of possible values that you don't have to worry about all of these different possibilities, you can use a smaller confidence interval, but it comes at the cost of having lower confidence. Okay, question, what are incorrect phrases to beware of when interpreting confidence intervals? Okay, so well, this slide, I think all of these are correct things to say, okay? So you can say 20% is not considered a plausible value, and we have evidence that P is a value different from 20%. Here we write, we cannot say that we have evidence that P is a value different from 25%. And here we can say, it's not evidence that P is equal to 25%. I'll show you a few more slides that talk about, what interpretations are not correct. So we've been talking about confidence intervals, and it's important that we use the phrase confidence, okay? So if we create a 95% confidence interval, our margin of error is around 9%, whereas if we create a 99% confidence interval, our margin of error is closer to 12%, okay, 11.8%. And so with the 95% confidence interval, our confidence in, we're confident that it's, basically 30% with a margin of error of 9%. So that takes us from 21 to 39%. And the 99% confidence interval is 30% with a margin of error of around, let's say, 12%. And so that goes from 18 to 42%, okay? And so with the 95% confidence interval, we have evidence that it's different from 20% because 20% is not inside the 95% confidence interval. Whereas with the 99% confidence interval, we don't have evidence that the proportion is different from 20%, okay? And the only difference between these two is the level of confidence. Okay, we're using the same data. We have the same standard error. We have the same sample proportion. It's just that because we have different levels of confidence, that changes our margin of error, and that changes the conclusion that we're able to make. At 95% confidence, we're more ready to kind of reject certain values. We're ready to reject the possibility of 20%. Okay, we're going to say that's not a plausible value. But on the other hand, if you want to be more cautious, right? If you want to be more confident in the answer that you're giving, that requires you to be a little bit more cautious before you reject any values. And so at 99%, if you want us to be 99% confident, we're not able to reject the possibility of 20%. Okay, and so so even though we are making different conclusions from the same data, those different conclusions are not in conflict. You know, these are the different conclusions that we would make based on basically our risk tolerances. Okay, at 99% confidence, we we want to be very confident in the answer that we give, and therefore we have to be a little bit more tolerant in terms of what values are possible. We don't want to reject, you know, a certain possibility. Okay, right? So it's like when you're making plans, if you have to kind of consider like every single possibility, it's going to make you a little bit more cautious, and you have to take into account that something, even if it's a rare circumstance, you have to take that into account, you know, it kind of to avoid disaster or something. So you have to kind of think about, you know, what's the consequence of being wrong, and if the consequence of being wrong is going to be a very costly mistake, you might need to go with a 99% confidence interval or something even higher in some cases, and then you would have to take into account, you know, many possibilities. Okay. On the other hand, if the consequence isn't that bad, you can get away with a lower level of confidence. You'll have a smaller interval, and you only have to plan for a certain, you know, just a few possible outcomes, right? Okay. When we make confidence interval statements, the statements that we make use the word confidence, right? So the confidence interval conclusion, when we make a 95% confidence interval, is I am 95% confident that the proportion of Netflix subscribers in the population is between 21% and 39%. Okay. What you don't want to say, and this would be an incorrect interpretation or an incorrect phrase to use, would be that there is a 95% probability that the proportion of Netflix subscribers is between 21% and 39%, okay? And these two statements feel very similar, where the only real difference is that this one says I'm 95% confident, and this one says there's a 95% probability, okay? And so, you know, when I first say this, a lot of students are confused because to them, the idea of being 95% confident was kind of, to them, was synonymous with the idea of that there's being there's a 95% probability, okay? And so what I'm gonna do is I'm gonna, you know, I left my coin. Let me go grab a coin here. Okay, so I've got this coin, and I'm going to flip it. Okay, and so I'll ask you a question, and this is not a trick question, but if I say, what is if I flip the coin, what is the probability that it will land heads? Okay, and you should be typing in 0.5 exactly, right, or 1/2. The probability that the coin will land heads is 1/2. Okay, so I'm going to go ahead and I'm going to flip it. Oh, shoot, I dropped it. Okay, And so now I've flipped the coin, and now I ask the same question. And I ask the question, what is the probability that the coin has landed heads? Okay, and your answer to this question, okay, so I've asked, what is the probability that the coin has landed heads? And you have some answer, okay? All right, now watch what I do, okay? I look at it, and then I cover it back up. And now I ask the same question, what is the probability that the coin has landed heads? Okay, and so maybe you feel awkward because I feel like I've asked the same question 3 times now. But the truth is that the last 2 questions were trick questions, okay? That after the coin landed, it was actually a nonsense question to ask what is the probability that the coin has landed heads? Because probability exists only for things that are uncertain, okay? Once the coin landed, it either landed heads or it didn't land heads. It does not make sense to ask the question, what is the probability that the coin landed heads? Because it either did or it didn't, okay? It made sense. It made sense to ask the question, what is the probability that the coin will land heads before I flipped it? Before I flipped it, that question made sense because we did not know what would happen, okay? But after the coin flipped and landed, asking what is the probability that it landed heads no longer makes sense because either it did or it didn't. You don't know how it landed, okay? You can't see how it landed. So all you can say is I am 50% confident that it landed heads. I'm 50% confident that it landed heads. But talking about the probability that it landed heads is a nonsense, is kind of a nonsense question because it either did or it did not. Okay, and so in the same way, when we are talking about the confidence interval, okay, that proportion, the population proportion P, it's either inside the interval or it's not, okay? It's some fixed value. It's a property of the population. If we could freeze time and look at everybody and, see exactly how many people subscribe to Netflix and know exactly how many people are in the population and get that proportion, we could get an exact proportion value, okay? And it's either going to be inside our interval or it's not going to be in our interval, okay? But we don't know what that value is. So again, it does not make sense to talk about probability. It only makes sense for us to talk about being confident that it's in our interval or it's not in our interval, okay? So, so when you talk about a confidence interval, it is wrong to say that there's a 95% probability that the proportion of Netflix subscribers is between here and here, because this proportion either is or is not in the interval, okay? And because we don't know what it is, we can say that I'm 95% confident, but we can't say that there's a 95% probability. Right? I hope that makes sense, okay? Because that's why I try to instill that we're talking about confidence levels and not, and we call these things confidence intervals and not probability intervals or things like that, okay? Okay. I am going to skip section 7.5 in the textbook, okay? So in the textbook, chapter 7, section 5, talks about comparing 2 population proportions with a confidence interval. I'm going to go ahead and skip that. We will see basically this kind of where we can compare 2 population proportions with a hypothesis test, and I'm going to skip the confidence interval. I don't feel like we're missing out too much, and I'm doing this in order to kind of make sure we have we can cover all the material we need to cover for this class. Let me give you the first quiz answer for today. So for today, it's week 4 Wednesday. Week 4 Wednesday. First quiz answer is B. B as in bear or ball. First quiz answer is B. Okay. All right, so now we'll keep going, and we are going to introduce hypothesis tests. Hypothesis test is chapter 8, and sorry, okay. So we'll introduce hypothesis tests in chapter 8, and we'll spend some time on this. So you know, this week you have a quiz that's going to be due on Friday. I got to get. Actually, I haven't posted that file yet, so so I will link to a Gradescope quiz for this week, and it will cover, you know, the content from this week, and we're going to spend time on hypothesis tests, which is chapter 8. I'm breaking up chapter 8 into 2 parts, so you'll get the first part today, and then the second part will be on Monday. So we'll get started here. Okay, and so you know, for hypothesis tests is another method for statistical inference. Okay, and statistical inference is the process of, you know, making conclusions about the population based on a sample of data. Okay, and we've learned the confidence interval already. That's one method for statistical inference, where we're making a conclusion about the population based on a sample. And then the other method that we'll cover in our class is the hypothesis test. Okay, and so hypothesis testing is a framework for us to kind of do statistical inference, for us to make conclusions about the population. We're going to learn 2 hypothesis tests in our class: the Z proportion test and the t-test for means, and that's and these are 2 of the most basic but most important hypothesis tests to cover. And you know, again, if you took another statistics course, you would probably learn more hypothesis tests. You know, there's a whole bunch of more tests that you can learn, but we're just starting you off with 2. And you know, even though they're kind of basic in nature, they are very important. Okay, you know, if you continue reading the textbook in chapter 10, you would learn something called the chi-squared test. You know, other textbooks will talk about kind of a correlation test and ANOVA and things of that nature. Okay. The important thing in a hypothesis test is that when you're doing research and you're doing science and you're asking questions, okay, whatever research question we have has to be turned into a what we call a testable hypothesis. We've got to turn our question into a statement that we can test. Okay, so we might wonder, is a particular drug effective at treating a disease? Okay, we've got to turn that question, you know, is this drug effective, into a statement that we can test. All right, and I'll show you how to do that. Okay, so you know, when we make these testable hypotheses, we can think of them as claims about the population. Okay, and we're always going to the hypotheses always kind of come in pairs. Okay, the first hypothesis that we make is going to be called the null hypothesis. Okay, and in order for it to be a testable hypothesis, it's going to be a claim that the population has some exact property. Okay, so you're going to see equal signs in the null hypothesis. It's a statement that says, you know, the population has this exact property. Okay, so for example, we might have a question and we might want to know if someone is playing with an unfair coin. Okay, that maybe it lands heads more often than tails. Sorry, I'm getting some feedback noise here. Give me a second here. Okay, so so perhaps we want to test if someone is playing with an unfair coin that lands heads more often than tails. Okay, so what we're going to do to make a testable hypothesis out of this is that we have to say that the coin in the population has some exact property. Okay, that the population of coin flips will have a certain exact proportion or property, and we're going to start by saying, you know what? Let's make the claim that the coin is fair. Okay, we're gonna say that the coin is fair, and it has the exact property that the proportion it lands heads is 0.5. Okay, and it seems a little counterintuitive because we want to know if the coin is unfair, right? We want to know if the coin is unfair, that it lands heads more often than tails. And I'm saying the claim that we have to make is that the coin is fair. Okay, so it seems a little counterintuitive. But the reason for this is that in order for it to be a testable hypothesis, we have to make a claim that the population has some exact proportion, okay? If we wanted to say that the coin is unfair, that the coin lands heads more often than tails, we would have to say something like the proportion it lands heads is greater than 0.5, that P is greater than 0.5, but that's not an exact statement because anything that comes in with P, like if I flip the coin, and it lands heads, say 6 times out of 10, does that mean that it supports this claim that the coin is unfair? Okay, or if it lands heads 7 times out of 10, it's a little bit tricky. And so what we have to do is we're going to start by making the claim that the coin is fair, that it has an exact property, that it's going to land heads exactly 50% of the time. Okay, and so one idea that I think is helpful is that when you make the null hypothesis, okay, the testable claim is that it's always going to have an equal sign in it. Okay, and then you pair the null hypothesis with the alternative hypothesis, which is going to be an inexact statement. And so in this case, the null hypothesis, which is the statement that we're testing, is that the coin is fair, and we're going to pair it with the alternative hypothesis that it's unfair and that it lands heads more often than tails, that P is greater than 0.5. Okay, and the logic that we're going to go through is that we're going to gather data, okay, and we're going to test this null hypothesis that the coin is fair against the data that we observe. All right, and so so we start off with this this null hypothesis claim that the coin will land heads with probability 0.5. And so what we're going to do is we're going to flip the coin a bunch of times, okay, when we gather our data. And let's say that we flip the coin, I don't know, 100 times or something, okay, or 50 times or whatever it is, okay. We flip the coin a bunch of times and it lands heads 60% of the time, okay. The coin lands heads 60% of the time. And this is how the test works, okay. If the coin were fair, okay, if we have a fair coin and we did a whole bunch of flips, what we would expect is we expect the coin to land heads 50% of the time, okay? We expect it to land heads 50% of the time. But what we observe is that it landed heads 60% of the time, okay? And so the question we're asking is this difference between observing 60% heads versus what we expected, 50% heads, okay, is that difference significant? Or could that difference be the result of randomness, right? Because every time I flip the coin, it's subject to randomness. And so, I could flip it 10 times and it could land heads 6 times out of 10. And I don't think anybody would say, well, it landed 6 times out of 10, therefore the coin must be unfair, right? Because we understand that just because that due to random chance, we could have gotten 6 heads out of 10 flips. That's not a strange outcome, okay? On the other hand, if I flip the coin thousands of times, and it landed heads consistently, around 60% of the time, then that would provide a lot more evidence that the coin is actually unfair, that it lands heads a little bit more often than tails. Okay, and so the answer of, is this difference between 60% or 50%, could that just be randomness, or is this an actually significant difference? And that's going to depend on how many times we flip the coin, right? So, so if we flip the coin 10 times and observed 6 heads instead of what we expect, which is only 5 heads out of 10, that difference between 60% and 50% is not significant, right? We would not say that it is, okay? And that this difference between 6 heads and 5 heads, that could just be explained away by randomness, okay? But on the, in contrast, if I flip the coin 1,000 times and it lands heads 600 times out of 1,000 instead of 500 times out of 1,000, because if the coin's fair, we expect something around 500, maybe give or take a few, but we're getting 600 heads, the difference between 60% and 50% is significant, right? Trying to claim that this coin is still a fair coin after it lands heads 600 times out of 1,000, that would seem highly suspect. That would seem, trying to claim that the coin is fair seems very suspect at that moment, okay? So, so we would not, we would say that we've got evidence that the coin is unfair, okay? And so, in these cases, I think we've got a kind of intuitive sense of the probability regarding our data. We can understand 6 heads out of 10, not unusual. 600 heads out of 1,000 would be highly unusual with a fair coin, okay? And what we want to do is we want to be able to answer the same kind of question for values in between, right? If I flip it 100 times and I get 60% heads, is that unusual? If I flip it, 80 times and I get 60% heads, is that unusual? Or what about 140 times, okay? Where do we draw the line? And we have an actual kind of methodology to go through in order to kind of help us guide our answers, right? So I kind of just want to pause here and just make sure. So I haven't done any real math. I've just kind of talked about these things, appealing to our intuitive sense of probability by saying this thing is likely and this result that, 600 heads out of 1,000 is unlikely. And I kind of wanted to make sure that that the reasoning and the logic here makes sense, okay? And if you have any questions, please give me a red X or throw a question in the chat. Or if all of this makes sense, you can give me a green check to let me know that that we're doing okay. Okay. Well, some of you guys gave me green checks, so I haven't seen any questions yet. Okay. Well, then I'll flip to our next thing, okay? And so what we're going to do is we're going to kind of formalize the hypothesis test and rather just rely on our kind of intuitive gut feeling. We're going to try to get a quantity, okay? That says, what is the probability of observing our data? What is the probability of getting the outcome that we've observed or something more unusual if the null hypothesis were true? Okay, so this is the question that we want to ask, that we want to answer. And the answer to this question, what is the probability of observing our data or something more unusual if the null hypothesis were true? This probability is known as the p-value, okay? The p-value is the probability of getting the outcome that we've observed, observing our data or something more unusual if the null hypothesis were true. All right, and we will formally go over the results here. okay? So we can, so, you know, for our example, we're talking about the probability of getting a sample of flips where only, where we're getting 60% heads, okay? Or something more unusual if the coin were a fair coin, all right? So we're gonna, what we wanna know, you know, if I go back here and I say, I flipped the coin 10 times and observed 6 heads, the p-value would be, what's the probability of getting 6 heads out of 10, okay, if this is a fair coin, okay? And if we say 6 heads out of 10, the true p-value actually is 6 heads out of 10 and everything else that's more unusual. So that would include the outcomes 7 heads out of 10, 8 heads out of 10, 9, and even 10 heads out of 10, because we want to know, you know, what's the probability of getting this outcome or anything even more unusual if the coin actually were fair, okay? On the other hand, if this was my data, I flip the coin 1,000 times and I get 600 heads, we can still ask the same question. What is the probability that we get 600 heads out of 1,000 coin flips, right? And I think just intuitively, we know that the probability of getting 600 heads out of 1,000 coin flips is going to be much lower than the probability of getting 6 heads out of 10 coin flips. And so, you know, before we have to do any calculations, we can just talk about the different outcomes that we could get, right? So one is that we do the calculations and it turns out that it's very unlikely to get our data if the null hypothesis were true, right? So it's, if we do our calculations with 1,000 coin flips, we would find that it's very, very, very unlikely to get 600 heads out of 1,000, okay? Or anything even more extreme, more unusual than 600 heads out of 1,000. Okay, because we're expecting something around 500 heads out of 1,000. And if we do go through the calculations, we're going to say, you know, it's almost impossible to get 600 heads out of 1,000 coin flips. Okay, meaning because that means it landed heads 600 times and tails only 400 times. So we're getting basically like a 20% difference. And I would say it's very unlikely to get our data if the null hypothesis were true. Okay. On the other hand, if we flipped the coin only 10 times and we got 6 heads and we did the calculations, it would turn out that it's not unlikely, okay? That there's actually a high probability of getting 6 heads out of 10 flips, okay? The outcome where the coin lands heads 6 times out of 10, that's not an unusual outcome, okay? And in that case, you would have a large p-value. All right. And so, so if we talk about outcome 1, all right, where it's very unusual, right? So if we do 1,000 flips and we get 600 heads, okay, we'll go through the calculations. It turns out if the coin truly is fair, it's very, very, very unlikely for the coin to land heads 600 times out of 1,000 times, okay? It's very unlikely if the coin were fair. But the fact that we actually collected this data, right? We actually did, what we're going to argue is that we actually did collect the data where the coin landed heads 60% of the time. We actually did get 600 heads out of 1,000 flips, okay? And our calculations say this should never happen, okay? But the calculations say it should never happen if the coin were fair, okay? It's very unlikely to happen if the coin were fair. And so the very fact that it did happen means that this, the assumption upon which we made these calculations was wrong, right? That because it did happen, then we must conclude that the coin is not a fair coin. And that's the explanation behind why we observed the outcome that we did. This is, the coin is not fair, and that's why I was able to observe 600 heads out of 1,000, okay? Because according to the calculations, a fair coin should almost never produce 600 heads out of 1,000 flips, okay? So therefore, the the claim or the belief that the coin is fair must be wrong, okay? So based on the evidence that we've collected, based on the data that we've collected, we can conclude that the coin is not fair, that the proportion P is not 0.5, but rather some other proportion that could actually produce a sample that's 60% heads, right? So perhaps the coin is unfair and the true probability that it lands heads is, I don't know, 58%, okay? And if the probability that it lands heads is 58%, then yeah, we could believe the outcome of getting 600 heads out of 1,000. Or maybe the true probability is 60%, okay? But we would have a hard time believing that the coin is a fair coin where it lands heads 50% of the time, okay? The other possible outcome is that the coin, that when you do our calculations, that the calculations say that it is not unlikely, okay? That it is not unlikely to get this outcome of 6 heads out of 10 flips, right? Whatever data that we have observed, it's not unlikely to get that result, okay? So we say the coin is fair, we've got a fair coin, and we ask, what is the probability of getting 6 heads out of 10 flips, okay? What's the probability of getting 6 heads out of 10 flips? It turns out, there's a high probability, okay? I don't know what the answer is, but it's not low. It's not low enough for us to say, for us to doubt this outcome, okay? So, yeah, when you flip the coin 10 times, you're expecting something around 50% heads, okay? But getting 60%, in this case, 6 heads out of 10, is not an unusual outcome, okay? And therefore, we have no reason to suspect that the coin is unfair, okay? It doesn't prove that the coin is fair, okay? It could be that the coin is unfair, and that's why we got 6 heads out of 10 flips. But with such a small sample, we can't make this conclusion, right? If you could talk about trying to like cheat at a casino, which definitely do not do, right? But if you want to go undetected as a cheater at a casino, the trick would be to not get greedy, right? If you only just play a tiny bit and you cheat just a tiny bit, and so you win, you walk away with just a little bit of extra money, the casino might not catch you, okay? But if you get greedy and you decide to play, hundreds of games and you're cheating and you win a whole bunch of those games, then the casino will know that you're doing something. They might not be able to see what you're doing with your hands or whatever, but they can say, based on the probabilities, this outcome should have never happened, and therefore we can be pretty confident that this guy is cheating, okay? But on the other hand, if a person's trying to cheat at a casino, all they have to do is maybe they actually are cheating, but if they only play a few games and they win like 3 games and they walk away without getting greedy, then it will be difficult for the casino to kind of catch that. And that's what we were saying here, okay? We flipped the coin 10 times, we got 6 heads out of 10, okay? 6 heads out of 10 is a little bit different from what we expected, okay? But it's not enough for me to just say, that's conclusive proof, or that's evidence that the coin is unfair. It's just saying that, okay, it's not that unusual. That could have just been good luck, okay? But at the same time, it does not prove that the coin is fair either. Is that all right as far as the reasoning here for hypothesis tests? Okay. All right, let me give you your second quiz answer for today, and then we'll go ahead and then we'll take a break after that. So our second quiz answer is A as in apple, okay? A as in apple for the second answer for today's quiz. Okay, why don't we go ahead and take a short break. We'll come back, I guess 11:05, and then we'll finish off the lecture. Okay, so all right, we'll continue on here. All right, so I got a question. It says, can you please clarify the reasons why comparing the sample sizes of 10 and 1,000 is important in this example? Those numbers are just arbitrarily chosen. I'm using 10 and 1,000 because I think we have an intuitive sense that if I flip the coin 10 times and if it lands heads 6 times out of 10, I don't think anybody would be alarmed by that situation, right? If you flip the coin 10 times and it lands heads 6 times out of 10, that would not seem that unusual, okay? And so if it lands heads 6 times out of 10, you would not immediately suspect that the coin is unfair somehow, that somehow the coin is, has been rigged to land heads more often, okay? Even though it's landing 60% heads, which is more than 50%, right? The coin should land 50%. It's landing 60% heads, 6 out of 10 flips. That's not unusual, okay? Whereas I'm just kind of appealing to an intuitive sense. I think if you flip the coin 1,000 times, if you flip a coin 1,000 times and it lands heads 600 times out of 1,000, that would seem highly suspect, right? That would seem like, okay, I don't believe that the coin is fair anymore, right? Because the idea of a fair coin landing heads 600 times out of 1,000 seems a little, you know, a little preposterous, I think. That's and I don't know, maybe I'm assuming a little bit too much regarding kind of our intuitive senses of probability, but getting 600, you know, 60 versus 40% for 1,000 flips, I think would seem really strange, okay? And so that's what I'm appealing to here. They're just kind of arbitrary numbers that were just either, you know, big or small that would either make us suspect or not suspect that, okay? I want to go over a couple more definitions before we get into a couple examples where we do some real numbers, and that will pretty much be it for today's lecture. Okay, when we talk about the null hypothesis, the symbol that we use is H0 or HO for the null hypothesis. Okay, and the null hypothesis is going to be a claim that the population has some exact property, right? This is the hypothesis that we are testing, and it's always going to have an equal sign, okay? And then the null hypothesis always gets paired with an alternative hypothesis, and we use HA for the alternative hypothesis, okay? So we've got HO and HA. Sometimes we call this H0 and H0, okay? But the alternative HA is, that's going to have either a greater than sign, a less than sign, or a not equal sign, okay? It's going to, the alternative hypothesis is actually going to look very similar to the null hypothesis, except we're going to replace the equal sign in the null hypothesis with either a greater than sign, less than sign, or not equal sign, okay? And, you know, what we use depends on how the question has been written, okay? The p-value, which we've talked about, that's going to be the probability of getting our data, okay? The probability of observing our data or something more unusual if the null hypothesis were assumed to be true. So if we assume whatever statement we made in the null hypothesis, if we assume that's true, we go through our calculations and we say, okay, well, what's the probability we get 6 heads out of 10 flips? Or what's the probability that, you know, if the coin were fair, we get 600 heads out of 1,000 flips or something more unusual? That's going to be the p-value. All right. Back here, you know, when we talked about the outcomes, we said it's very unlikely to get our data that we have a small p-value, or it's not unlikely that we have a large p-value, okay? Now, how do we decide whether a p-value is large or small, right? 6 heads out of 10, we said, well, that's not unlikely. We're having a high probability there. 600 heads out of 1,000 flips, that's very unlikely. We have a very low p-value. We have a very low probability of getting that outcome, okay? But what if we have something kind of in between? How do we decide whether this calculated p-value is large or is small, okay? And for that, we have to kind of draw an arbitrary line. We draw an arbitrary line that we call alpha. It's called our significance level. And that's going to be the kind of the value that we use to just decide whether the calculated p-value is large or small. It is an arbitrary value. It's something that we just choose. Most frequently, we choose alpha of around 5%. That's kind of the value that statisticians have generally agreed upon for quite a while. You know, that number of 5% is coming under scrutiny, you know, in more recent years, but that's kind of where we are right now. Okay. And so, you know, when we talk about the alternative hypothesis and whether we should use a greater than, less than, or not equal sign, this brings up the issue of whether our test is a one-sided or two-sided test. Okay. And it comes down to, part of our definition of the p-value is that when we talk about calculating a probability, it's not the probability of just our exact outcome in our data, but anything also more unusual. So when we talk about getting 60% heads in 1,000 coin flips or 10 coin flips or whatever, however many coin flips we have, it also includes, we're going to say 60% or more heads, okay? Because we're asking for something more unusual than what we've observed, right? So if we're dealing with a one-sided test, then the alternative hypothesis will have either a less than sign or a greater than sign, okay? If the alternative hypothesis has a less than sign, when we use what we mean by more unusual means that we're getting whatever value that we have in our sample statistic, or something less than, okay? So this is unrelated, okay? But let's say you're in a situation where you're expecting to get a proportion of 60%, okay? So let's say we're talking about, you know, what proportion of people, I don't know, went to the dentist last year, okay? And so maybe we're expecting that proportion to be 60% or something, okay? And we go and we calculate, gather some data, and our sample comes back with only 40% of the people went to the dentist last year, okay? And so when we do our calculations of a p-value, it's going to be, you know, what's the probability of getting a proportion of only 40% or something smaller, something more unusual, if the kind of the true value was 60%, okay? On the other hand, if our alternative hypothesis has a greater than sign, more unusual means whatever our statistic was, or something even larger than that. So if we're expecting a proportion of 60% in our population, and we get a random sample where that proportion is 80%, the p-value is going to be, you know, what's the probability of getting a proportion of 80%, or something even larger if the null hypothesis, if it truly were 60%, okay? The not equal sign, includes more unusual on the greater than side and more unusual on the less than side as well, right? So continuing kind of this scenario where we're expecting a proportion of 60%, and let's say our sample proportion ends up being 80%, okay? We say, well, 80%, 0.8 is, you know, 0.2 or 20% away from what we expected, okay? And so the p-value that we're going to calculate is the probability of getting a proportion that is 20% or more away from what we expect. So we're going to look at what's the probability of getting 80% or something larger, that's more, you know, 20 percentage points or more away from what we expected of 60%, plus the probability of getting 40%, which is 20 percentage points away on the other side, 40% or something even less, right? You know, I'm throwing a lot of kind of ideas and theories at you. I think it will make a little bit more sense with a few examples. And then, you know, when you do your homework this week, I'm hoping it will kind of solidify the ideas here, okay? You know, take your time working through the homework this week before you attempt the third quiz. You know, last quarter, students, I think, you know, quiz 1 and quiz 2, I think a lot of students felt like they were pretty easy, okay? And quiz 3, I think, is straightforward, okay? I'm not trying to throw anything that's tricking you, but it does require a little bit more thinking through and more reasoning through than maybe quiz 1 and quiz 2 did. And so, so I don't want these to catch you off guard, okay? So let's work through a couple hypothesis tests as an example, okay? And so finally, we will get to try to answer this question, this example that I think I brought up, you know, a couple of weeks ago, right? So we first saw this and we talked about, you know, some kind of carnival game where you spin a wheel and half of these spaces are marked with winner spaces and half of them are marked as losing spaces, okay? And so, you know, if the game is fair, when we spin the wheel, we expect to win half the time, right? That's what we expect, right? If 6 out of 12 are win and 6 out of 12 are lose, we would expect to win about half the time. So our friend goes, and I don't know who goes to the amusement park and plays those little carnival games this many times, but let's say our friend plays 25 times. He's really trying to win whatever, you know, giant stuffed bear there is or something, okay? So he plays 25 times and he only wins 8 times. And so he's upset, right? He says, I think the game's a scam. I played 25 times and I only won 8 times, right? If the game's fair, we would expect him to win maybe 12 times or 13 times, something around there, okay? And he only won 8 times, which is less than what we expected, right? So if the game is truly fair, he should win 12 and a half times, okay? And we know 12 and a half times is not actually possible here. It's either gonna be 12 or 13, but you know, if we play 25 times, we should win about 12 and a half times, and he only won 8 times, which is less than what we expected. So does that mean the game is a scam, okay? Or is the game actually a fair game and it's just random coincidence, or in our case, bad luck, that our friend only won 8 times out of 25, okay? I'm just curious, what's your gut feeling on this? What's your gut feeling? Do you think the game is unfair? And I'm just curious. This poll costs no points or anything, but if you think the game is unfair, click yes, and if you think the game is not unfair, click no in the participant thing, right? So he won only 8 times out of 25. Do you think that's evidence that the game is unfair, or do you think this is just the result of bad luck? Okay. All right. Well, thank you to those of you who participated. Seems the class is kind of split around 25%, 75%, at least for those who responded. So some of you think maybe the game's a scam, 8 out of 25, that's pretty low. Or maybe it could just be chalked up to bad luck. Okay, well, what we're gonna do is we're gonna do some calculations here, okay? And so we're gonna actually go through the hypothesis test. All right, so when we create our hypothesis, this is our hypothesis. We're gonna say that the probability of winning the game, every time you play the game, it's a fair game, you have a 50% chance of winning. Okay, we're gonna say P is equal to 0.5, right? And then in our case, we wanna test the possibility that the game's a scam, okay? That somehow, whatever they did something to the wheel so that when you spin it, it's actually not going to land heads, or it's not gonna go to win 50% of the time, but it's gonna be something less, okay? And you know, the carnival games at an amusement park, there's no gaming commission that says that the people have to play fair, right? So if you go to Las Vegas and you gamble, there is the Nevada Gaming Commission, and they are very strict, and they make sure they check all of these things to make sure that, you know, there is a game that where you spin the wheel, and they make sure that the wheel spins fairly, that, you know, when you throw dice, that it is fair, and that, you know, if you play a slot machine, that the slot machine, you can look up the numbers on the slot machine to find, you know, the exact kind of payout probabilities, and it's very tightly regulated. But you go to an amusement park and they have kind of that, you know, midway section where they have all those little carnival games. That's not regulated. They can be scam games if they wanted to be, and there's no nothing you can really do. But anyway, this is what we've got. Either the game is fair, or maybe it's unfair. Or if you go to Chuck E. Cheese, which is basically a casino for kids, those games, the games that do tickets, those don't have to be fair either. I don't know. There's this thing where the lights go in a circle, and you can time the buttons exactly, and it intentionally just there's actually a dial. There's Mark Rober on YouTube like explored this, and there's actually a dial that you can kind of crank how often it should win or lose. Same thing with the claw games. Those games are all scams. I mean, you can play them and have fun, and I just want you to be informed about the entertainment value that you're getting, right? If you say it's worth $3 to try out the claw game for fun, go for it. But you should be informed that they have been rigged so that, you know, a bunch of time, you know, the payout probabilities are such that the machine is going to be profitable. Okay. So anyway, what we're going to do is we're going to pick a significance level. And the most common choice is we're going to say 5%. Now, how do we come to 5%? I don't know. This is just kind of something that has been agreed upon. I think it's because we have 5 fingers that we just said 5%. Probably should be something around there, but you know, and depending on how kind of confident you want to be, you can choose alpha equal to 1%. That's also another common choice. That's a little bit more of the cautious approach if you have a lower alpha. And you know, in some cases you could choose an alpha greater than 5%, but I'd say that's fairly rare. Okay, I'd say it's fairly rare to use an alpha greater than 5%. Okay. Our hypothesis test depends on using the central limit theorem. We're going to use the normal distribution as an approximation for the sampling distribution. And so we have to kind of check our conditions there, which are the random and independent condition. All right, so we can assume this is met because, you know, if we're playing the carnival game, each of those games are going to be independent of each other. Okay, and then our sample is large enough, right? So our n is 25. The probability of winning is 0.5. So n times p is 12.5. And n times 1 minus p is also 12.5, and both of those numbers are greater than 10. So our sample is large enough, okay? And there's, we don't have to worry about the big population condition because we are not sampling from a finite population without replacement. We're just spinning the wheel. And so technically we could spin the wheel infinitely many times. And every time we spin it, the probabilities don't change. So this is not something we have to worry about. Okay, so what we want to do is we want to compute, calculate the p-value, all right? And the p-value is, you know, the probability of getting our data, which is 8 wins or something more unusual. So that would be 8 wins or less if the null hypothesis were true, if the game were fair, right? So our data is we won only 8 times out of 25. We got a p-hat of 0.32, okay, right? 8 divided by 25 is 0.32. And if the null hypothesis were true, we expect our p-hat to be around 50%, okay? And so we want to know what's the probability of getting a sample where p-hat is 32% or less, right? Because if our friend is suspecting that the game is rigged for winning only 32% of the games, you know, he would suspect if he wins anything less than 32% as well, right? So we only won 32% of the time. So what we're going to do to answer this is we're going to use the central limit theorem and the sampling distribution of p-hat. And we're going to say, okay, well, if the game is fair, we expect we would expect to get a p-hat of around 50%. So we would have our mean set to be 50%. And our standard deviation is, 0.5 times 1 minus 0.5 divided by 25. And we calculate that out. Our standard error comes out to be 0.1, okay? So, so we do this, okay? And so if p hat comes from this normal distribution, then we can calculate a test statistic z, right? So what we observed is we observed only 8 wins out of 25, okay? And that's a 32% that proportion is 32%. We're expecting 50%, and we only got 0.32. We divide that by our standard error, and so we get a z-score of negative 1.8. Okay, z-score of negative 1.8. And so if we go to the z-table, right, we go to, here's the z-table, and I look up negative 1.8, that probability is 0.0359, okay, 0.0359. I just remembered something funny about Chuck E. Cheese. Apparently, well, I don't know, this is completely unrelated. I think Chuck E. Cheese rebranded under Pasquale's Pizza. Did you guys hear about this? Like in lockdown for like DoorDash, nobody wants to order takeout from Chuck E. Cheese, right? Like you go on DoorDash, you're not going to pick Chuck E. Cheese for pizza delivery. So they renamed themselves Pasquale's Pizza, which is like the mascot. They have like the little animatronic things, and so anyway, they named themselves Pasquale's on DoorDash so that people might actually order pizza from them. You're getting the junky. I went there like not too long ago with my daughter, and I was like, this is the worst pizza. Yeah, anyway, sorry. If you work for Chuck E. Cheese, my bad. But anyway, okay. So we look up, did they go bankrupt? Yeah, the kids caught on. No, I don't know. Okay, we're getting more background on the Pasquale's was a chain from the South. Interesting, and the pizza was bad. Well, if Chuck E. Cheese used their recipe, yeah, it was not a good pizza. Anyway, sorry, I don't know how we ended up there, but so we do our calculations, and it says, all right, well, what's the probability of getting this result, right? If the game were fair, right? If I flip this coin, or not flip the coin, but if I play a fair game 25 times, could I just win 8 times out of 25 just by bad luck? And it says, yeah, that could happen. How often does it happen? It happens about 3% of the time, okay? 3.6% of the time. And so now that we have a choice, we say, okay, so you played the game 25 times, you win only 8 times, and you go, man, I either got really bad luck, okay, or the game is rigged against me, okay? And so the probability of getting only 8 wins out of 25 due to just bad luck alone, just random chance alone, that's going to happen 3.6% of the time, okay? And so, so we have to, so our p-value comes out to be 3.6%, and we have to make a choice, right? So if the game were fair, there's only a 3.6% chance that someone playing the game would win only 8 times or less, okay? And so when we drew this kind of arbitrary line in the sand, and we said, hey, if it comes in less than 5%, we're going to say our p-value is classified small, okay? And so, it is possible, technically it is possible to win only 8 games or less by random chance. We're going to say, 3.6% is low enough where I'm going to say, I don't think it was bad luck, okay? It could be. I mean, I could be one of those unlucky 3.6% of people, but I don't think so. Instead, I'm going to think that the game was rigged, okay? And so, so the fact that we actually did observe a sample where we won only 32% of the time, okay, 8 times out of 25, indicates to us that the claim that the game is fair, that claim is wrong, okay? And instead we conclude that the game is somehow rigged against us, that the game is not fair, and maybe they've tweaked the wheel somehow so that that it produces less than 50% wins, okay? And that would explain why we only won 8 times out of 25, okay? So so that's that, okay? So, you know, in our case, that's if we're choosing an alpha of 5%. Now, if you want to be more confident, right? Because now we want to file a complaint against the amusement park or something and say, hey, this game is unfair. But there's no Nevada Gaming Commission for amusement park games. So, but anyway, you want to say, hey, this game is unfair or something, and you want to kind of get upset. You know, maybe we should be a little bit more cautious, and somebody might say, like, you know, before I accuse anybody of being unfair, maybe we should gather more data, okay? And so somebody else could be working with a lower alpha, maybe an alpha of 1%, and that way, you know, you could be a little bit more sure that you're not making some kind of mistake here. All right, is the reasoning here okay as far as this the steps that we went through? We said, you know, I'm expecting this kind of proportion, and this is what I observed. What I observed is lower than what I expected, and so we do the calculations to say, you know, what's the probability of getting what I observed? And that probability comes in low. We say, we conclude that that the game is not fair. Okay. All right. Here's let me do another example here. Okay. And so, you know, I think we just responded to the census, and well, you know, we'll see what happens. There's all kinds of issues with the census, which is a problem, but hopefully we can still get an accurate count. All right, so in the last census, which is already 10 years ago, you know, in Los Angeles County, we had a senior population of around 20.2%, okay? And so for the purposes of the census, there's different definitions of what a senior is, but I think for the purposes of that thing, a senior was anyone aged 62 or older, okay? And they accounted for around 20.2% of the population in Los Angeles County, okay? And so let's say we go out and we do a survey, and somehow we select 150 random people from the county, all right? And we find that 36% of the people that we surveyed are seniors, okay? So 36 out of 150, okay? And so does this survey provide evidence that the proportion of seniors in the county has changed, right? So it used to be 20.2%. You know, we haven't conducted the census yet, but we're just like kind of doing some initial polling, and we're going to do 36 out of 150. Does that mean that the proportion has changed, right? So, so when we set up our null hypotheses, we're going to say, all right, the null hypothesis is that the proportion has not changed, that P is still 20.2%, that it's still 0.202. And then the alternative is that the proportion has changed. And when we say has changed, that means that proportion could have gotten bigger, higher than 20%, or that proportion could have gotten lower than 20%, 20.2%. Okay, and so here, we're not going to use P is greater than or P is less than. We're going to just say P is no longer equal, not equal to 20.2%. So we're going to say P not equal to 0.202. And it would be interesting to us if the proportion of seniors got bigger, and it would also be interesting to us if the proportion of seniors got lower. And what we're doing is we're checking out our data, which was 36 out of 150. So before we get into any calculations, we'll pick our significance level. And so we'll just continue to use alpha equal to 5%. And then we'll check our central limit theorem conditions. And so, you know, the sample says the people were randomly selected, so that condition's met. The large sample condition, we have to check to see if our sample is big enough, all right? And so if the null hypothesis were true, then our P is 0.202, and we took a sample of 150. So we do 150 times 0.202, and we get 30.3, and we do 150 times 1 minus P, so 0.798, and we get basically 120, 119.7. Okay, and both of these numbers are bigger than 10, so we're fine, all right? And the big population condition is that, you know, you're not supposed to sample more than 10% of your population. So as long as our population is bigger than 1,500 people, you know, our population is big, okay? And so LA County has about 10 million people in it. So this condition is met, right? So LA County, it's just one county, but it's got a lot of people. We're like bigger than a whole bunch of states. Okay. And okay, so now we'll go through the calculations. What is the probability of observing our data or something more unusual if the null hypothesis were true? Okay, so our data is that n is equal to 150 people and we have 36 seniors. So we get a p hat of 36 divided by 150. We get a p hat of 24%, right? And we want to know, okay, 24%, that's a little different from what I expected. In the census, we got 20%, 20.2% of the population of seniors. In my sample, I got 24%. That's a little higher than what I expected, right? Is this difference, though, is that significant? Going from 24% versus 20.2%, is that difference significant? So, so we're going to ask, what is the probability of getting a sample of 0.24 or something more unusual? And more unusual in this case means, okay, 0.038 away from 0.202, right? So 24% is about 3.8 percentage points higher than 20.2%. So we want to know what's the probability of getting a proportion that's, you know, 3.8 percentage points or more away from 20.2. So that means 24% or higher, and then whatever 20.2 is minus 3.8 percentage points. So that's what, 18.4%, something like that, okay? So if the null hypothesis were true, we would set up our sampling distribution and we say, okay, we expect p hat to come from a normal distribution where the mean is 0.202, okay? And then the standard error, when you do the calculation, is gonna be 0.0328, okay? Our standard error is p times 1 minus p divided by n square root, okay? And that turns out to be 0.0328. All right, so this is what we have. We have p hat is equal to this. And we're going to calculate our test statistic. Okay, hang on, I'm getting a question here. It says, how did we determine that this example was a two-sided test and not a one-sided test? How do we know to use a not equal and not a greater than or less than sign? Okay, so let me just go back and answer this question. So the question is, why am I using a not equal sign here for our alternative? And how do I know that this is a two-sided test? Okay, so the question, the way the question is written is, do the survey results provide evidence that the proportion of seniors in the county changed? Okay, here changed is not indicative of saying, like, do we now have evidence that there are more seniors than we did 10 years ago? Or do we have evidence that there are fewer seniors today than we did 10 years ago? We're just asking, did the proportion of seniors change? Okay, and did it change means it could have gotten bigger or it could have gotten smaller, and either of those results would be interesting to us. And so we want to consider it being higher than 20.2% and also consider the possibility that maybe the proportion got lower than 20.2%. So to consider both of those, I'm going to use a not equal sign. If I was only interested in one thing, where, you know, I'm trying to make some kind of narrative that our population is getting older and we're gonna, I don't know, run out of Social Security money or something, I don't know, whatever I want to, you know, you could just test only one hypothesis and you can say, well, do we now have evidence that the population is getting older, that the proportion of seniors is increasing, okay? And then you would have a one-sided test, okay? But here, yeah, we're interested in either possibility, okay? So anyway, we say, you know, p hat would come from this normal distribution, which we've determined from the central limit theorem. that the mean is 0.202. Okay, if the null hypothesis were true, I would expect random samples to still produce a mean of 20.2%. I got a sample where the proportion is 24%. So we're going to take that difference and we're going to divide by the standard error, which we calculated, and I get a z-score of 1.16, a z-score of 1.16. Okay, and so I'm going to look this up on the table, and what I have to do is my p-value has to be the probability that z is greater than positive 1.16, and because it's a two-sided test, it's also going to include the probability that z is less than negative 1.16, right? So I find this value of 1.16, and I want to get the probability that z is greater than 1.16 because we've got a two-sided test, so we want to include 1.16 or more extreme that way, which is 1.16 or more positive, and also the other side, negative 1.16, and things that are more negative. So what I'm going to do is I'm going to just take the area of one of the tails and multiply it by 2. So when you go to the z table, you can just look up negative 1.16, which is 0.1230, and multiply that by 2. You can also look at positive 1.16, subtract that from 1. So you do 0.8770, 1 minus 0.8770, and you get the same thing, 0.1230 times 2. And we get a p-value of around 24%, close to 25%. So my p-value is almost 25%. And so what this says is that, and so here's our conclusion, if our sample is 24% seniors, okay, which is higher than what we expected of 20.2%, right? So the census 10 years ago said the proportion of seniors is 20.2%, and when we took a random sample, we got 24%, right? And when we do the calculations, we got a p-value of close to 25%, 24.6%, okay? And so that means even if the county's senior population is still 20.2%, okay, there is around a 25% chance, 24.6% probability that a random sample ends up being 24% seniors or something more unusual. It's just a coincidence that this number 24% is close to this number 24.6%, close to our p-value. That's just a coincidence, okay? But we're just saying that there's about a 1 in 4 chance that a random sample ends up being 24% or something more unusual, okay? And so if our significance level is 5%, this outcome of getting 24% seniors is not considered unusual, okay? So even though it's a little bit different from what we expected, we were expecting around 20.2%, it's not considered to be an unusual result, okay? And so our conclusion is that the survey does not provide evidence that the proportion of seniors has changed, okay? So we're gonna say we don't have evidence that the proportion of seniors has changed, okay? We can't say that it stayed the same, right? Again, it doesn't mean that the proportion has stayed the same. It's just that we only took a sample of 150 people, and that's not enough evidence or not enough data to make a conclusive statement. So maybe the proportion of seniors is the same. Maybe it's changed. Maybe it's changed just a little bit, okay? Maybe it's changed a lot, but we just don't have enough data yet, okay? All right, we have a question that says, are we comparing the p-value of 0.246 to the alpha value of 5%? Yes, okay? So when we use alpha equal to 5%, we compare this p-value of 0.246, 24.6% versus 5%. And because 24% is bigger than 5%, we're gonna say our p-value is large, and therefore our result is not unusual, okay? In the other example, when we were talking about the game, okay, our p-value came out to around 3.6%. We compare that to our alpha, 3.6% is less than 5%, okay? And so we say this is an unusual outcome, right? This is unlikely to happen. 3.6% is less than 5%. It's an unusual outcome, and therefore we conclude that the game is unfair, okay? So, so hopefully these examples will help you kind of guide you through some of the problems that you'll encounter in your homework and on the quiz. And that's all I've got for you guys today. So we'll end our lecture here, and we'll see you guys next Monday, or we'll see you guys on Monday. Have a good weekend, and yeah, good luck on your homework and also the quiz, and I'll make sure I get that quiz link posted. Oh, I never gave you the third quiz answer. Thank you for that. The third answer for today's viewing quiz is E as in elephant. E as in elephant. Okay, E as in elephant. The question here says, could you go over again why you use the two-sided test for this example? The two-sided test, again, is because I'm interested in any kind of change in the proportion of seniors, okay? I would be interested in the proportion of seniors being higher or the proportion of seniors being lower, okay? As far as the game, the spinning wheel game, and I said we have a one-sided test, I would only be interested if the game was found to be rigged against the players, right? If somehow the carnival game was set up in such a way to help the players win, that would not be upsetting to me as the player, right? And so I'm not interested in the outcome that the proportion is greater than that. Okay. All right. So we'll end here, and yep. Good luck, you guys, and we'll see you guys on Monday. Have a good weekend.